Log normal versus normal distribution. While a normal distribution is symmetric, a log normal distribution is skewed to the right since it runs from a finite point up to positive infinity. And you can see that right here. So k represents a finite beginning point, and on the plus side, this variable can have a value all the way up to positive infinity. So a good illustration of log normal distribution is security returns. So if we form a distribution for discrete returns, its lower bound would be finite at minus 100%, while its upper bound will be positive infinity, as there's no limit as to how much return you can make on a stock. Well, that's true, right? So if you buy a stock, what's the worst thing that can happen? You can lose minus 100%. So you see how you have a finite negative value for stock return. On the other hand, in theory, there's no upper limit with respect to how much return you can make on a stock. So it can go to positive infinity. So since the positive outlier values are much larger, the distribution gets pulled to the right, in other words, towards the positive side, thus resulting in this skew shape. And there it is. This asymmetry will form the log normal distribution displayed above. Now, however, if you take the natural logarithm of these discrete returns, we will find that the distribution will stretch from negative infinity to positive infinity, thus forming a normal, i.e. bell-shaped distribution. So here's what it's saying. These are discrete values, so that it's minus 100% if you're sort of looking at discrete returns. But if you find the natural logarithm of these discrete outcomes, then the result, in other words, if you plot the natural logarithm of all these values, then you would actually get a normal distribution. In other words, you'd get that symmetric bell shape. And here it is. To illustrate, suppose that the stock price falls from $100 to $2. As a result, the discrete return would be minus 98%. So that's discrete, without continuous compounding. However, its logarithm would be as follows. So to find the logarithm, here's what we do. We take the natural logarithm. We just say 2 over 100. And how we got that is the following. The 2 is the ending value, and then we divide it by the beginning value. So what we're doing is we're calculating the rate of change going from 100 to 2, but using continuous compounding. And so when you find the logarithm of the percentage change, it works out to minus 3.91. And when you convert that to percent, that works out to minus 391%. So even though, let's keep it simple, the discrete return, so actually let's keep it even more simple. We have a stock that went from $100 to $2. If you use discrete compounding, that's a loss of minus 98%. If you use continuous compounding, that's a loss of minus 391%. So you could see where discrete actually has a finite point, therefore resulting in this log normal distribution. When you take the natural logarithm, you can see that the numbers are actually approaching negative infinity, and therefore the natural logarithm is starting to exhibit a bell shape, i.e. going from negative infinity to positive infinity. So this example illustrates how the logarithm could reach negative infinity. The relationship between a log normal distribution and normal distribution then is follows. A random variable follows a log normal distribution, in this case the discrete returns, if its natural logarithm, i.e. continuously compounded return, is normally distributed. And therefore, the opposite is true. If the natural logarithm of a random variable is normally distributed, then the random variable itself must exhibit a log normal distribution. And ladies and gentlemen, not to be confused, so let's go back to this framework. So here you have a log normal distribution. Make no mistake about it. You can spot a log normal distribution because it's skewed. And all it's saying is if you take the logarithm of all these values, In other words, if you use continuous compounding, this would actually translate into the bell shape. So then it's just a matter of going back and forth. So if you take the logarithm of this, it'll be normally distributed. On the other hand, if the natural logarithm of a random variable is normally distributed, then you know that the random variable itself would have a log normal distribution. So just to end our observation, therefore, a log normal distribution may be completely described by the mean and standard deviation of its natural logarithm. And basically what that last statement indicates is the following. So if we're given this information, so if we're given the natural logarithm of that random variable, we just need to know what the mean is and the standard deviation is of this symmetric distribution or normal distribution. And equipped with that information, we can work backwards and actually plot out the discrete values for the random variable itself. So let's just use our stock return. So if we are given the continuously compounded rates of return, now remember, when you're using continuously compounded rates of return, the distribution would be symmetric. So if you give us the average return and the standard deviation of that continuously compounded rates of return, we can actually work backwards and plot the discrete returns. But when you plot the discrete returns, it'll be normally distributed.